Hello, my name is Andrew Jackman, and I will be presenting an overview of the preference learning module of our for-all system. To get started, we're using a collaborative filtering method, which evaluates user preferences for a product through the ratings of other users towards that product. Basic versions are user-based filtering and item-based filtering. The former involves finding the preferred item based on the active user's relationship to other users, while the latter looks at the items that the active user likes and looks at the relationship between that item and other items to determine if a new item would be desired. While these models provide a good baseline, we need something more advanced to handle the wide variety of users and items that will be available within our system. To accomplish this, we use a factorized neighborhood model that utilizes both an item-to-item and a user-to-user relationship algorithm to determine user preferences. This model integrates both an enhanced form of singular value decomposition, SVD++, as well as a neighborhood model. A quick breakdown of the algorithm is as follows. R hat sub UI is the preference that a user U has for a given item I. We calculate this value by taking mu, the global average of the user's preferences across all items, and adding B sub I and B sub U, which are the deviations from the average value for the item I and user U. We then add a normalized value determined by the ratings of similar users. This value is generated by the difference between the user's actual rating of the item, RUJ, minus the baseline rating of that item, BUJ, which becomes a scalar multiplier for two factorized quality vectors, QI and XJ. Then additionally, we add QI times YJ to capture implicit data from user ratings. The user-to-user relationship is defined in a similar fashion, but instead of iterating over every rating of every user for the item, we iterate over every item rated. And there is no additional implicit information to capture, which simplifies our algorithm. Instead of training a user-to-user and item-to-item model separately and then combining them together later in the post-processing stage, a more principled approach optimizes the two models simultaneously, letting them know of each other while parameters are being learned. Throughout the entire training phase, each model is aware of the capabilities of the other model and strives to complement it. With this in mind, we can sum those two equations from the previous slide here. Here's an overview of our design. Starting from the left, we take in the initial data and use it to construct our user-to-user and item-to-item similarity matrices. Using these similarity matrices as a baseline, we resolve the cold start problem and can construct an initial user-to-item preference matrix. This initial matrix is then sent as an input to another function to learn the various model parameters to produce the predicted ratings and minimizes the difference from ground truth via stochastic gradient descent. Then the updated predicted ratings will be passed to the learning and decision-making groups. Explicit feedback from users, when available, is processed and becomes part of the updated preference matrix as part of updating parameters. Since we are the first module in the for-all system, we receive all of our initial inputs from the environment. These inputs are CSV files containing the demographic information for each user, as well as each user's explicit preferences. From this, we provide a matrix containing the ratings each user has for each item to the other components. In order to construct this user rating matrix, R hat, we iterated over a baseline model of SVD++ provided by Surprise, which is a Python scikit for building recommendation systems. This initial SVD++ model provided a great starting point, but our model needed to support for factorized neighborhood approach, which resulted in our NSVD++ or neighborhood SVD++ variant. Our final iteration of the model adds in support for the cold start problem, as well as a way to account for user-to-user similarity. In order to handle this user-to-user functionality, we needed to construct a user-to-user similarity matrix. Our initial demographic information had the potential to be missing many values, and when using the cosine similarity, the standard for this kind of process, we cannot arbitrarily fill in missing values for fear of affecting the results. Instead of calculating the entire similarity matrix in one step, we find the similarity between each two users independently of the rest and drop any aspects that either are missing before proceeding to the standard cosine similarity function. The individual similarities are then stored into a user similarity matrix for easy access. We also utilize an item-to-item similarity matrix, but since there is no potential for missing values in this data, we only perform some simple data preprocessing, which consisted of normalizing each item based on the unit size, then based on the L2 norm, before finding the cosine similarity between each item. In order to perform our evaluation, we needed to collect data about our users. This was done via a Google form document, which the class filled out. The survey asked for various demographic information, as well as some initial preferences of users. Item information was scraped from the US Department of Agriculture and organized by the nutritional breakdown of each item. In the end, we arbitrarily chose 19 items to be used by the system and acquired demographic information from the entire class, which consisted of 16 students as well as the professor, for a total of 17 users. From these values, we constructed user-to-user similarity and item-to-item similarity matrices. We performed a visual evaluation of the contents, and everything held up to our inspection. Our primary evaluation was done on predicted user ratings, R hat, and to accomplish this, we split the data and iterated over various hyperparameters with the goal of minimizing the root mean squared error of the model. These hyperparameters were the minimum number of ratings for a user or item before the model shifts from using similarities to learned parameters, the number of epochs of learning, the number of features, and the set of data that was used for training. This last parameter is tested in multiple ways, the first of which was using a random percent of the data, the second by moving a specific number of rows or users from the training set to the test set, and last by moving a random number of columns or items from the training set to the test set. The results of our updated model were unfortunately underwhelming. While we did improve from the baseline in every test set, we only decreased error by an average of 0.035. We consider this a success for our model, albeit a very minor one. To wrap up, we acknowledge that there are some significant limitations of our model, given the data available. Because of this lack, we cannot say with certainty how good or bad our model is with overfitting. There is a distinct lack of granularity in the results. As far as future corrections for our component, we have a few different ideas. First and foremost would be providing a tighter integration between our component and the other components in the system. This would allow for faster testing between components and help decrease the turnaround time from one iteration of the system to the next. We also see a way to optimize the model by separating R hat for each food group to allow for more precise comparisons and recommendations. Lastly, getting the system tested on unknown populations, as well as a larger scale population, would provide more validity to our approach and potentially provide us with better results than we saw in the previous slide. This concludes our presentation on the preference module of the 4L system. Thank you.